Okay, quick check 6.2. So we're talking about changes in state here. So think like a solid going to a liquid, liquid going to a gas. And a lot of times we're talking about water, but we can do it with different substances. So the first question up here is changes in state. You want to look at that and say, okay, for each one of these, what do we call it? And is it exothermic or endothermic? So solid going to liquid, melting. You might say fusion, but that's not very common. Gas going to liquid, okay, we're talking about condensation. Liquid going to solid, freezing. Or if we're talking about something hot, maybe solidification. And liquid going to gas, okay, that would be vaporization. Or evaporation. Or you might even say boiling. So any of those would be great answers. Okay, now for whether it's exothermic or endothermic. Okay, solid going to liquid. Okay, it should be kind of clear. We got to put some heat into the solid in order to get it to become a liquid. I'm just going to use H because I don't have very much room. Okay, so that is going to be an endothermic process. Okay, gas going to liquid. Okay, remember heat always goes on the more solid side. Okay, so if I had to put heat into my liquid to get it to become a gas, so we can see that that's going to be exothermic. And that's the kind of say that I don't think really makes a lot of sense physically to think of it forward. Gas going into liquid gives off heat, but heat going into a liquid would go to gas. That makes sense. Liquid and solid. Okay, again, heat would go on the side of the more solid side because I had to put heat into a solid to get it to become a liquid, just like number one. So this guy would be exothermic as well. And liquid going to gas, again, I'd have to put energy into my liquid side to become a gas. So that's going to be endothermic. So those are important. Okay, next little piece is talking about heat of fusion and heat of vaporization. So again, if we take kind of a definition of heat of fusion and heat of vaporization, think of it as how much a substance resists change in state. Now, when we were talking about C sub P, we were talking about how much does it resist change in temperature, but now we're talking about how much does it resist change in state? How much does it want to stay a solid or stay a liquid, not change into something else? So let's take our little stories. Samples of solid ethanol, where it's got a number of 26 calories per gram, and ice, which is 80 calories per gram, which is bigger, have the same mass, were heated at their melting points, which will require less energy to melt completely. Well, the one that requires less energy is the one that has less resistance to change, so it's going to be the one with the smaller heat of fusion, so this 26. So the answer is going to be the ethanol. The ethanol will require less energy to melt because it has a smaller heat of vaporization. Second one, when samples of liquid propane and liquid ethanol were heated with 400 joules of energy at their boiling points, twice as many grams of propane vaporized as ethanol. Twice as many grams, okay, which has the higher heat of vaporization. So the higher, who is resisting change more? Okay, well, if twice as many grams of propane changes ethanol, then the ethanol is the one that's resisting change more. So ethanol is the answer in this case. So ethanol is the answer in both questions. Now we get to the calculations. Okay, for these heat calculations, the formula we're using, okay, is the fact that the Q, the heat, is equal to the mass times the delta H, heat of fusion or heat of vaporization. So that's a little bit different, a little simpler than the one where we were heating things up, where it was Q equals M delta T C sub P. This one is Q equals M times delta H, that's all. Because you can tell mass is going to be grams, and we're going to multiply by joules per gram, and the grams drop out. We're left with joules, which is heat. So show your work for each problem. Okay, what is the value of Q when 70 grams of steam condenses at 100 degrees Celsius? So here we have our formula. And since we have the formula, then we know these are our three variables we're looking for. And one piece we have to start with and says, are we going to be talking about heat of vaporization or heat of fusion? Okay, which of these two numbers do we need to use? And the word is condenses. That's our clue word. Condensing, we know, means gas going to liquid. So we want the gas-liquid change. We're talking about vaporization. So the delta H is the delta H of fusion, and the number we're going to use is 2260 joules per gram. Now we can figure everything else. What's the value when 70 grams, so that's the mass, of steam condenses at 100? Okay, at 100, we don't really need to use that number, okay? It's just that's the proper way. That's when steam is going to condense. It's going to boil at 100, it's going to condense at 100, so that's, that's the proper number to use in the problem, but we don't need it mathematically. Okay, we're looking for Q. Now notice also that since this is condensing, it's going to give off heat, so really the value is going to be negative Q. This delta H is actually negative 2260, but you can put that in later. Okay, to finish the problem, we have to substitute in. So we're looking for Q. So Q is equal to mass 70 grams times 2260 joules per gram. Okay, we can call that negative if we want to. And when we do the math, I get 158,200 joules, because grams drop out, and we're going to make that negative because it's heat given off. Okay, so we can either say that, this is the energy is negative 158,200 joules, or we could say that it's 158,000 joules given off, released. Okay, the other problem, what mass of water freezes when 400 joules of energy is released? Okay, so let's get ourselves a new color. Okay, so we're talking about freezing. So freezing is solid and liquid, so we're talking about the heat of fusion. Okay. Let's go back here. Okay, this was condensing, so that was the heat of vaporization. Okay, so this is the heat of fusion. So the delta H we're talking about here is delta H of fusion. Okay, I knew I did it wrong. Okay, so this was supposed to be vaporization. I used the right number, but I gave it the wrong label. So back to here. Okay, heat of fusion, and the heat of fusion we know is 330. And here's the problem. On some of our handouts, we're saying 333, and then we're saying 334. So, use whichever. You're going to get a close answer. What mass of water freezes when 400 joules of energy? So it's 400 joules, and we're looking for the mass. So now we can substitute in. So we have 400 joules equals the mass times 333 joules per gram. Now we do math. Okay, so I want to divide both sides by 333. And so my answer is going to be 400 joules divided by 333 joules per gram. So I'm going to end up with grams on top. And the number will be, get 1.20 grams. That would be good. Okay, so I get 1.2 grams. That's how much water would freeze when 400 joules of energy is released. Now, since the energy is released, we could call that a negative 400 if we want to, but that's not important right now. Okay, next problem. The heating curve. Okay, heating curves, we say that, when you are warming something up, and getting it to melt, those are two different things. Warming and melting, warming and boiling, okay, they happen differently. So these things have a shape like this. It goes this way and then this way where it's melting, this way and then this way where it's boiling, and then goes up like that. Okay, so that's the basic shape we want to do. So we're going to say we're going to have some ice at negative 20, and we're going to go up to steam at 150 and identify the states in each segment. So I'm going to do a bigger version. So we're saying, well, let's put in our marks, and we know that ice melts at 0. So I'm going to put that in so I have a reference line. And we know that it boils at 100. And if we don't know that, then get that in your brain, because that's important stuff for water. And then we're going to put our numbers in. So we're going to say that we're starting at negative 20, so we'll start low. And it's going to warm up, warm up, warm up. Okay, so this is temperature over on this side, and this is the heating time on this side. Okay, until it gets to 0, and then once it gets to 0, it's going to plateau out. It's going to stay here until everything has melted. After everything is melted, then it's going to warm up, and it's going to warm up until it gets to 100. At that point, it's going to plateau again and stay there until everything has melted. And then after that, it's going to warm up again So we get this kind of look to it. And let's go ahead and label everything. Okay, we know down here this is solid. We know this is liquid. We know this is gas. So here in the middle we have solid and liquid. And here we have liquid and gas. Okay? And just to add to this, you know, when we do these slanty parts, okay, so here and here and here, then if we had to calculate, we're doing Q equals M delta T CP. And when we're doing the flat parts here, okay, those flat parts are the Q equals M delta H. So this one here would be M delta H of vaporization, and down here would be Q equals M delta H of fusion. So we're going to use one of these two things. So when we were talking about our lessons, on the first lessons of, you know, how do you get the energy of something warming up, then we're talking about these parts of the heating curve, and then now that we're in second part where we're talking about the energy for a change of state, then we're talking about this equation. Now I have one really nice picture that I found on the internet, okay, and it shows, you know, solid. It's just our heating diagram. But what I like about it is that it shows the pictures here. So here's a solid, okay, we know solid all lined up, and it's going to require energy to separate the solid into the liquid. So here's our in-between part where we have some solid and some liquid. And then we get to the point here where it's all liquid. So while it's liquid, okay, then the Q is equal to M delta T C sub P. And then we're going to vaporize, and here then we have some liquid, some vapor, okay, and so the temperature, the energy that we put in is not going to change the temperature, okay. The energy we put in goes into separating these particles. And then once they're all separated, okay, everybody's a gas, then we could warm them up again. And then again we have Q equals M delta T C sub P. So in these states here, okay, in the just one state, then the energy going in gets to speed them up faster and faster and faster. And then in these in-between parts, okay, then the energy going in doesn't speed up the particles, doesn't change the temperature, it changes the state. So again, this is a change in temperature, this is a change in state. This is a change in temperature, this is a change in state, and this is a change in temperature. And that's the first two lessons.